Hi everyone, so I'm going to talk through 26.7, which is radioactive isotopes in use. I'll just adjust the screen slightly for you. Okay, so radioactive isotopes in use. So we use radioactive isotopes, or scientists do, to basically age things. So this mummy is made of living material, and so you could use carbon-14 to date it. Carbon-14 is a radioactive isotope of carbon. So you need to be able to determine the half-life of the sample from a log graph, be able to describe the process of radioactive carbon dating, be able to describe the medical applications of radioactive tracers. We looked a little bit at the end of last lesson about how to plot this graph. So the decay curve for the number of isotopes that have decayed would be a curve. So if we take logs of this, we get this. Okay. If I rearrange that to look like y equals mx plus c, so if I plot log n on my y-axis, this is count rate, but remember you can substitute n for activity, count rate, corrected count rate, and mass, okay? You then have your y-intercept would be log of the original number here. Your gradient would give you the decay constant if you plot t on the x-axis, okay? So for example, so that shows you there, your gradient would give you the decay constant, and then your y-intercept would give you natural log of the original number of molecules. So let's say this number here that you read off the graph was 60. That number isn't the original number of molecules, it's the log of the molecules, the natural log. So to get the correct answer, you would then need to get rid of the log, and to do that you do e to the power. So if you want to get rid of this, e to the power log n0 is equal to log 0, and then you do e to the power 60 here, and that gives you 1.1 times 10 to the 26. So if a question asks you for the initial number of radioactive isotopes and you've got a graph like this, just remember the y-intercept is the log of the original number, and to get the answer you need to do e to the power of whatever that y-intercept is. So carbon dating. Living plants and animals contain this small percentage of radioactive isotope carbon-14. It occurs when cosmic rays remove neutrons from the nucleus, and the neutrons collide with nitrogen nuclei to form a carbon-14 nuclei. So here's the neutrons colliding with nitrogen. Okay. They make carbon-14 and then a proton. Now this radioactive carbon-14 is taken into from the atmosphere into plants by photosynthesis. It has a half-life of 5,570 years. So within the lifetime of a plant, there's actually negligible decay. Once the plant has died, no more carbon-14 is taken in, obviously, because it's not photosynthesizing anymore, and it will start to decay. And the activity of the dead sample enables its age to be calculated. Basically then, anything that eats plants will then have this carbon-14 inside them, and also anything that takes it in respiration as well. So it gets into any living material. So you find a sample of dead, here's an example. You've got a sample of dead wood, it's found to have an activity of 0.20 becquerels. And an equal mass of living wood is found to have an activity of 1.3 becquerels. Calculate the age of the sample, give your answer to three significant figures, and it tells you the half-life of carbon is 5570 years. So you can try this on your own if you want. The answer is 12,300 years, or you can press pause and do it yourself, or you can do it with me. Okay, so if you're doing it with me, write down what you know. So this is what we know. from the question, A0, A and T half. I'm going to convert T half into seconds. You don't actually have to do this because you're getting your half-life is in years and your answers in years. You could actually just leave it all in years. However, if you're not sure, convert to seconds. So that's it in seconds. T half, so 5,570 years, 360 times 365 days in a year, times 24 hours in a day, times 60 minutes in an hour, times 60 seconds in a minute. Then we want to find lambda. So lambda is natural log 2 over T half. So substitute your previous answer into there, but use the full one. That gives you lambda. Then I'm going to use this equation. We want to find T. So we need to rearrange it for T. This is the rearrangement. I did go through it previously, and I do go through it in another video to show you how to go through the answers. If you're not sure about this, let me know and I'll do a Google Meet and show you how to do it, okay? But I have shown you before. So I'm going to substitute all my values into here. Natural log A over A0 divided by lambda minus lambda. It gives you this many seconds, which you can then convert to years. Like I say though, if you had just left this as years, substituted that into there, you would get the decay constant per year. And then in this equation here, you would just put whatever that value is per year in, and you would get this answer out. So if you want to, you can prove to yourself that you can do that. So another type of dating is argon dating, and the half-life is much longer, so it's not really suitable for living organisms or things that used to be alive. So it's used to date rocks. Ancient rocks contain trapped argon gas as a result of the decay of the radioactive isotope potassium. It occurs due to electron capture of an inner shell electron, and as a result, a proton turns into a neutron. So basically, an inner shell electron is grabbed by a proton and it's turned into a neutron, and then a neutrino is emitted. So we did that in particles. This is that process in form. So you've got the potassium grabbing the electron, becomes argon, and then this neutrino is released. Now that so this potassium 40 isotope also decays by beta to form a calcium isotope, and this process is 8 times more likely than electron capture. So you've got two processes going on at the same time. You have this process of electron capture, and then you have this process of potassium 40 decaying by beta minus. And this one is 8 times more likely than this one. So what that means is 8 of these occur for every one of these. So if I started with 9 potassium 40 nuclei, 8 of them would turn into calcium and 1 of them would turn into argon. If I started with 18, 2 of them would be argon and 16 of them would be calcium. Okay. Now, this half-life by beta decay is 1,250 million years. So you can see that it's not really suitable for living things because I'm not sure how long living things have been around, but not much longer than this. So the age of the rock from when it solidifies can be calculated. So we use this to age rocks. Now, this is what I've just talked about, for every potassium 40 nuclei present, if there is 1 argon atom, there must have been 9 original potassium 40 atoms. So what that's saying is if you go and dig up a rock and you find 1 argon present, it must have been there originally 9 potassiums, because 8 of them would have been turned into calcium. So if you go and dig up a rock and there are 2 argons present, you would have had 2 argons, 16 calciums and 18 potassiums. So it's working on a ratio there. So how do we use this in a question? So the radioactive decay equation can be used to find out the age of the sample. So we're going to use n equals n naught e to the minus lambda t. So 4 potassium 40 atoms are now present for every 1 argon atom in a certain rock. So a scientist has gone and got a rock. They've found out there's 4 potassium atoms for every 1 argon atom. So if we go back here, this rock has still got potassium in, 4 of these for every 1 of these. It doesn't tell us about the calciums. Okay, so the number of undecayed nuclei would be 4, because we've still got 4. And we've also got 1 argon for 1 argon. And if we had 1 argon, then we'd have 8 calcium. Going back to this idea here, that we have 1 of these to 8 of these. So in our rock, we've got 4 of these. That's our number of undecayed nuclei. We have 1 of these, which must mean we have 8 of these. So our original number of nuclei would be 13, because we would have had 1 create this and 8 create this, and then you've still got 4 left over. So 1 went to create argon, 8 went to create calcium, and 4 haven't done anything yet. So our undecayed nuclei is 4, but our original number of nuclei is 13. Okay, this is all by ratio. We want to find the age, so we need lambda. So we're going to use our T half here. I've left this as years, so you can see it's different to the carbon 14 one. Natural log 2 divided by T half gives me 5.5 times 10 to the minus 10 per year. Substitute into here, okay. Need to rearrange for t, so I've got natural log is n over n naught divided by minus lambda. Because this is in per year, my answer will be in years, and my n is 4, and my original number of nuclei is 13. So substitute all in there, okay, and I get 2.130 million years, which is the answer. Okay. There's loads of information about radioactive tracers in the book. So a radioactive tracer is used to follow the path of a substance through a system. Its half-life has to be stable enough for the necessary measurements to take place, but short enough to decay quickly after use. It must emit beta or gamma radiation, so it can be detected outside the flow path. So it needs to. You might use it to detect leaks in underground pipes, or you could investigate uptake of fertilizers by plants. You can monitor the uptake of iodine from the thyroid gland. So loads of uses of this. It's also really exciting. You can model as oil reservoirs mathematically to improve oil recovery, which is actually what one of my ex-students does now. Other uses, you can measure the piston wear in engines. So if you inject, they have this radioactive metal ring, and as the ring slides along the piston, radioactive particles are transferred to the engine oil, and the mass of the radioactive material in the oil can be monitored and the rate of engine wear worked out. So incredibly sophisticated use. You can monitor the thickness of foil, so you fire beta through the foil. If the thickness gets too thick, then the beta is absorbed. You can use it for power sources. And there's a question on that in the book. And then there's a little part here about calculating energy. So if you're given the activity, then the amount of energy you produce would be the energy of one decay times the activity. And then you can substitute that equation in there. And again, there's another question on that in the book. Okay, so I want you to have a go at the questions, and I might put an exam question for you to have a go at as well. Any questions, let me know. Thank you. Bye.